You have reached the final assignment for the week. Before tackling this video, which deals with more compound probability, make sure you are done with Monday through Thursday's work as it leads up to today's lesson. Homework, Module 5, Lesson 7, or that 30 minutes of Imagine Math. Today we are going to continue, as I just said, with calculating probabilities of compound events. You guys are going to be able to calculate probabilities of compound events by creating and analyzing tables, lists, and tree diagrams. And your goal is, again, you'll have a Quizizz. You're looking for that 80% or higher mark. And our standard still is the same as Thursdays, which deals with finding probability of compound events. Just a quick reminder of probability. This has been on every slide since the start of this module. And we will jump straight in. So I just want you guys to listen and look and pay attention here. We're going to address this as we've been doing at the very end of the lesson. But this is the kind of frame that I want to put your mind in as you go through today's learning. So Talia is playing a game in which she must choose option 1 or option 2. And those two options are listed here. And then spin the game wheel. Flip the coin and roll the number cube labeled 1 through 6 for her to win a prize. All the conditions listed under her chosen option must occur. Which options should Talia choose? So I want you to think about that first. She should be choosing whatever option has the greater likelihood of occurring. Now, today we are going to work on calculating the actual probability, because remember, probabilities represent the likelihood something's going to happen. But overall, if she knows her math here, she'll be able to calculate these two different options and their likelihood of happening, or their probability. In this case, compound probability, because there's 3 events happening instead of just one. There's more than one, in this case exactly 3, as I said. And pick the one that's more likely to happen, therefore she has a greater chance to win. Okay? Now, we are going to spin on over to our video.
How can a model help you find the probability of a compound event? Think about this question during the lesson. Sadie has 1 ticket left at the school fair, and she hasn't yet won a prize. She decides between 2 games. Which game should she play? Let's think about how we calculate probability. Does having more possible outcomes make it more likely or less likely that Sadie will win?
Let's just think about this logically. Does having more outcomes or less make it more likely? Well, the less possible outcomes you have, the less likely you are to pick or have an outcome that doesn't result in winning, right? Say we have a bunch of marbles in a bag. If there are only 3 marbles and you're looking for one of those 3, you have a more likelihood of winning, or a higher likelihood of winning, than if you're looking for a 1 specific marble and there's 20 in the bag. Now, to be clear, having more outcomes doesn't always hurt if the added outcomes could also lead to winning. In fact, that would increase the likelihood. Okay? What do I mean by that? Well, if we have that same marble question, but I add more marbles in, but I say like it can be green or red, and I continue to add green and red in, that increases your likelihood. But overall, more outcomes will make it less likely because it's increasing the sample size.
For our first step, let's focus on the game Flip to Win. We can use a table to determine the probability of winning a prize playing Flip to Win. The first flip will be either heads or tails. The second flip will also be either heads or tails. So there are 4 possible outcomes. And there's 1 favorable outcome, 2 heads. What is the probability of winning a game of Flip to Win?
Select your answer.
All right, so in order for her, I think her name was Sadie, to win this, we need the probability of getting heads and heads, back to back. Well, we have a sample size of 4, so that is our total amount of outcomes, and we only have one favorable outcome. So that is a probability of what's going to be 1/4. Another way to look at this, which would take away having to do this table, is you can really multiply the probabilities. What do I mean by that? We have 2 flips of a coin. We are looking for heads the first time and heads the second time. The probability of getting heads the first time is 1/2. Just like the probability of getting heads the second time is 1/2. 1/2 times 1/2 gets 1/4. So, multiplication of those individual probabilities, this probability and this probability, will also get your overall compound probability. Now, that does not mean you don't have to draw the table, write the list, or use a tree diagram, but I do want you understanding that multiplication of individual probabilities also leads to a compound probability.
Divide the number of favorable outcomes by the number of possible outcomes. The probability of 2 heads is 1/4, or 25%. Now, let's use a second table to determine the probability of winning a prize playing flip and spin. Spinning the spinner has 4 possible outcomes: red, yellow, blue, and green. Flipping the coin has 2 possible outcomes: heads and tails. Our table shows each of the 8 outcomes of this compound event.
Now, this is a nice, neat, organized table here. Our sample space is 8. But remember, we could also use multiplication to think through this. So we are going to select each favorable outcome in the table, or select each outcome in the table to pick which ones are favorable. So let's click this first one. This is no prize. Okay, if we land on red and get a heads, that does not meet the qualifications. Neither does this one. And it's actually updating over here, which is pretty cool. Neither does this one. Neither does this one. So we're 0 for 4 so far in our trials, our sample space. This is a winner. We have blue and heads. So now we're 1 out of 5 based on what I've looked at. That's no prize, no prize, no prize. So we only have one favorable outcome here out of the 8 possibilities. 1 out of 8. Now, we multiply these individual probabilities. The probability of flipping a head is 1 out of 2. The probability of spinning blue here is 1 out of 4. 1/2 times 1/4 is 1/8. So that multiplication nets the same answer as simply creating a table, or if we created a tree diagram, or we created just a written out list.
Only one of the 8 outcomes is favorable, meaning there's only one way to win a prize playing flip and spin. This outcome is blue on the spinner and heads on the coin flip. The probability is 1/8, or 12.5%. Now we're ready to compare the probabilities of winning each game. The probability of winning a prize at flip to win is 25%, while the probability of winning a prize at flip and spin is 12.5%. Sadie is more likely to win a prize playing flip to win, so she should use her last ticket to play this game. Now you know how a probability model, like a table, can help you find the probability of a compound event.
We are transitioning to the part where I'm requiring you, the expectation is you are writing these notes down so you have them as a reference when you guys need it. Keep in mind, this is being recorded, so you can always pause and rewind as you guys need. Don't think you got to go all the way through super fast, particularly if you don't understand. Well, that said, if you feel like you got it fully, go through at your own pace. So what is the probability that a coin, so that is a, I'm going to use green today, that a coin, so that's a 50-50 thing, heads, tails, flipped 3 times will land heads up exactly 2 times. All right. For this one, I cannot use just that kind of multiplication trick because we're looking for exactly heads twice. We're not having two separate or three separate individual probabilities that we can just multiply together. This problem's a little bit more complicated than just multiplying 1/2 times 1/2 times 1/2. Okay? So, what I'm going to do is I'm going to use a tree diagram. I'm going to create it vertically, but tree diagrams can also be created horizontally. Now, let's say on our first flip, we have two possible outcomes, right? We could get heads, we could get tails. That's it. There's no other option. Don't say, well, it could land on its side, maybe, but very low possibility or chance that happens. Now, if I'm creating a tree diagram, I am going to branch off of this. I'm going to try to create these as neatly as possible. And let's say I flip heads. The second time, I could get heads or tails, right? And then if I branch off here, let's say I get heads, heads, then the next time, so my third flip, I could get heads or tails. Now, I can start, and I'm not anywhere near done with this tree diagram, but what I can start doing is I can start writing this first outcome here. This one over here is heads, heads, right? Heads first, heads second, heads third. This next one is heads, heads, tails, right? We got heads, heads, and then tails. Now, looking over here, I did not even finish this branch yet because this is only two, heads, tails, and we need three separate events happening here, three flips. Now, just like every other flip, this can be heads or tails. So what do we have here now? We have heads, tails, heads. And then over here, we have heads, tails, tails. I'm just following the branches. Heads, tails, tails, or heads, tails, heads, down here. I'm not done because I have to do this whole other side now. So let's create our branches off kind of here. I'm going to even make it, let's see. And I have a picture of this after to make it even neater. But let's say I flip heads or tails the first time. The next time it can be either heads or tails. That will be my second flip. Then after that, my third flip can once again be heads or tails here. Or over here, it can also be heads or tails. Now I can create my remaining sample spaces here, my possible outcomes. Tails, tails, heads. Tails, tails, tails from this one. Then over here I have tails, heads, tails. And then I have tails, heads, heads, just going straight this way. So overall here, I have 1, 2, 3, 4, 5, 6, 7, 8 outcomes. That does come from a half, and a half, getting 8 in the denominator. But the numerator isn't necessarily 1, which is what creates the problem here. Now, heads exactly 2 times. I'm going to just use my highlighter here, and I'm going to look for heads exactly 2 times. All right, 1, 2, 3. So we have 8 total outcomes. We have 3 that meet the criteria, 3 that are favorable outcomes. So that is a probability of 3/8, which is equivalent to 375 thousandths, which is equivalent to 37.5%. So that is an unlikely representation because that value is less than 50%. It's not impossible because it's not 0 though. Now, this is a neater representation. I hope that one day I can make tree diagrams like this, but I'm not the most artistic person. And here you have the visual representation of heads and tails based on an actual penny being used here. But what you have is really the same mathematics here. You have 8 equally likely outcomes, and 3 of the 8 meet the criteria of exactly 2 heads. The order of the heads does not matter. It's just saying, in general, it needs to be 2, whether it's the first 2, the last 2, or a mix-up of the first and the last one. It just needs to be 2 heads. All right, let's look at this next problem. The names of all middle school students with perfect attendance are entered into a drawing for one of 2 tickets to a baseball game. This year, Angie, Phil, Mark, Carly, and Josie attended school every day. So those are the perfect attendees. What is the probability that Mark's name will be drawn to win one of the 2 tickets? What I'm asking you guys to do, and then we're going to go over it, because I'm pushing you guys to really practice. That's going to lead to the results. I want you to try making an organized list of all the possible outcomes for the winners. So, maybe you want to make a column, right? Let me scroll down here. Maybe you want to make a column that just says Angie, right? And maybe that represents Angie winning that first ticket. So then maybe it would be Angie for the first ticket. And then the second ticket, let me see, Angie and Phil, right? Then maybe it's Angie and Mark, right? So on and so forth. What I am going to tell you, something that needs to be very clear, I'm going to use the highlighter. One of 2 tickets. They cannot win both tickets. So, you should not under this write Angie and Angie. They can win one of the 2. They cannot win both. So when you're creating your sample space, make sure you do not have the same name written 2 times next to itself, because that's not going to fit the problem. Now, if it said that Angie or anyone could win both, then you would have to include Angie and Angie as a possibility, but that's not the circumstance. So I want you to make an organized list of possible outcomes for the winners of the 2 tickets, and then try to answer our question, which says, what is the probability that Mark's name will be drawn to win one of the 2 tickets? Check the video when you are done with that. Now, instead of me creating an ugly organized list and being kind of disorganized, we have this, and me trying to write it out, we have this here. I got you started on this one. What you see highlighted in green is anywhere Mark's name appears, because we want the probability that Mark's name can be drawn to win one of the 2 tickets. So Mark's name appearing is the favorable outcome. Now, our total number of outcomes, I'm not going to count each individual one. Instead, I know there's 4 here. So 4, 8, 12, 16, 20. I'm just going to skip count by 4, multiply 4 times 5, rather than just go 1, 2, 3, 4, 5, 6, 7, 8, right? Work smarter, not harder. So our total number of outcomes, which goes in the denominator, is 20. And wherever Mark is, the number of favorable outcomes goes in my numerator. 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 20. That is his probability of getting one of the tickets. That can be simplified to 4 tenths, which is equivalent to 4 tenths, which is equivalent to 40%. So that's not a bad likelihood. It's still unlikely, but it's not dramatically low. It's pretty close to a 50-50 shot. Because there weren't that many kids, 1, 2, 3, 4, 5, who got perfect attendance out of all middle school. That's actually very low. That's concerning, but nonetheless, his percent chance is pretty decent because they only have 2 tickets, right? And for him to have almost a 50-50 shot at winning one of just 2 tickets is not bad at all. 40% chance, still unlikely, but decent chance. Next example, you're going to pause the video, you're going to write this one down. This question acts as a compare and contrast type question. Brazil has a number cube labeled with numbers 1 to 6 and a spinner with 3 equal sections labeled A, B, and C. How does the probability, and I'm going to try to color coordinate these for you guys. I'm going to use green here. How does the probability of rolling a number greater than 4 on the number cube and the pointer stopping on B? That's our first kind of comparison. And then in blue, I'm going to do compare with the probability of rolling a number less than 4 and the pointer stopping on C. Now, I'm going to use green with the green and then blue with blue. They're going to be different shades, but you guys will be able to make the connection. I'm going to use the multiplication approach. Since these are independent events, they're separate events happening. They don't affect each other. I can find the probability of both and multiply it together. I can also create a table, which I'll show you in a second. I could also technically create a list or a tree diagram. Rolling a number greater than 4. Okay. There is 5 and 6 on this dice that are greater than 4. That is 2 out of 6. That is that probability. Now, I'm going to simplify, because if I simplify before I go to multiply, my numbers will be smaller. So that's that first probability. And the pointer stopping on B. Well, there are 3 equal sections. B makes up one of the 3, so that's 1/3. So what I have here is 1/3 times 1/3, which gets 1/9. So that's the probability of the green one, okay? They both happen to be, the two parts of that compound probability happen to be the same fraction. Compare with the probability of rolling a number less than 4. Okay. The numbers that are less than 4 are 1, 2, and 3. So that is 3 out of the 6 sections, which simplifies to a half. Now, the pointer stopping on C, well, C makes up 1 section out of the 3 total. That gets 1/6. Now, I'm good with my fractions, and you guys are too, or you should be, hopefully, if you've been working at them. I know you guys have been. The bottom one, the one that's in blue, is a higher probability. Fractions are greater if the numerator is the same. The denominator being smaller makes the fraction overall bigger. Having 1/9 of something is much smaller than having 1/6 of something. Think of cutting a pizza into 9 slices and only taking 1 versus cutting a pizza into 6 slices, the same size pizza, and taking 1. You'll get more pizza in the bottom. So, Brazil has a greater chance of rolling a number less than 4 and the pointer stopping on C. Now, looking at the list approach, all I'm going to do is color coordinate the first one, find that probability, and then look at the second one and find that probability so I can compare. So we want greater than 4 and B. So we want on B greater than 4. I'm just going to go straight to this B row, and it's these two, 1, 2. So that represents 2 out of 3, 6, 9, 12, 15, 18. So that's 2 out of 18, which simplifies to 1/9. See how that multiplication got the same answer? Now, probability of rolling a number less than 4 and C. So I'm going to C, that's less than 4, that's less than 4, and that's less than 4. Automatically, I can tell that this second probability is greater because it covers more of the sample space, 1 more. But that also has a probability of 3 out of 18, which simplifies to this 1/6. There's a connection there, okay? I'm not saying just multiply. And in fact, if you're not 100% sure why I could multiply this and why I couldn't multiply, let's say, this one, I would stick with the organized lists and tree diagrams until you are clear at a deeper level why you can just multiply. Okay? All right, so back to this one. I know this video is going a little long, but I want to make sure at the end of the week you are good with your compound probability. If I'm looking at this spinner, okay, and I'm just going to use this multiplication approach here. And I'll use option 1 first. The wheel lands on S. Well, now I have to count all these sections. That kind of sucks, but I'm not going to complain. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That is 15 sections. The probability it lands on S is 1 out of 15. And I'm just going to double count that to make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yep. Now, probability that any coin lands on heads is 1 out of 2. And the probability that an even number is rolled is half of the numbers on a dice are even. 3 out of 6 of them. So, all I would really do here is I would do, and let me make this blue, I would do 1/15 times 1/2 times 1/2. And that gets a value of 1/60th. Not very good chance there. In case you're wondering, that value is like 1.5% approximately. It's 1 2/3%. That's very unlikely. Now, let's look over here. Z, I only see once as well. So let's make that 1 out of 15 here. Same probability here. So we're on the same starting point. Now, the coin lands on 0 sides is either side, is 2 out of 2. It's going to land on one of the sides. So that has a probability of 100% or 1. And the number 3 is rolled. That is 1/6 because there's only one side that has a 3 on a dice out of 6. All right, let's color coordinate and get this multiplication happening. So we got 1/15 times 1, which you don't even need because multiplying anything by 1 does not change the value. And what we're going to end up here is with 1/90th. That is even a worse percent chance. So option 1 is actually the better option here, but neither is particularly good. I would recommend her not play this game if she wants to actually win something. All right, this is just a quick key concept, kind of key point slide with compound probability. I'm not going to read this to you. You guys can pause and look over this. And then I will post another Khan Academy video for you guys to reference if you are stuck with compound probability of specifically independent events. The previous Khan Academy video on Thursday was on like tree diagrams and representations of compound probability. And then today's goal, knock out that Quizizz. It is labeled Calculating Probabilities of Compound Events. Once you're done with that, and hopefully you've already finished everything through the week, you're done for the week. Make sure you look at your tracker to make sure you're actually done for the week. And then you only have your next work on Monday.